Welcome back. This part 4 is the main part of this mini course, and I'm going to discuss McBrien-Spencer's proof. Okay, and this is Professor Tom Spencer. Okay, so this is what we are going to prove. So we are going to prove a bound on the correlation function for the XY model in 2 dimensions at vanishing magnetic field. And lambda L simply denotes a square lattice, L by L square lattice. This is the set of bonds and with periodic boundary condition. And theta is a collection of these spin variables, which runs between 0 and 2 pi. This is just the integration over all theta u. And this is our Hamiltonian. Now we don't have this magnetic field term, so I just omitted h here. And this is our partition function. This is a definition of thermal expectation value. Okay. And now this is the theorem. So for any beta, we have this upper and lower bound for this 2-point correlation function. And actually, the lower bound is basically trivial, but I'm going to prove this in part 5. Okay, of course, the main result is this upper bound, and it says that this decays at least with this power law. Okay, and of course, this is not optimal for high temperature, but it's sort of optimal for low temperature and for any UV. And here, eta beta is some strictly positive quantity. And for low temperatures, we have some control on this eta beta. Okay, and this theorem applies not only to the XY model, but it applies to the Heisenberg model and other models which have higher symmetry than the XY model. And it can also be extended to quantum spin system. So this is a very strong general result, but this is a paper. Okay, it only consists of 4 pages, and they are proving something else here. So the main proof is, I think, here. So as you see, this is one very good example of short, elegant proof that leads to physically meaningful, very strong result. Okay, so since this is so elegant, I wanted to discuss this, and I made this video. Okay, so of course my lecture is longer than this, but anyway, it's not very long. Okay. Everything is based on this simple lemma about analytic function. So let fz be an analytic function of z, which also satisfies this periodicity. You can think about cosine and things like that. And then you have this identity. And here you're just integrating on the straight real line. And if you shift it by phi like this, the result is the same. And here phi is any real quantity. And the proof is very easy. So since this is an analytic function, you can modify the integration path like this to get the same result. Okay, and then this path consists of 3 parts, 1, 2, 3, 4. And well, this 3 is something you want. And if you recall periodicity, then you easily find that this here and here are the same, and so they cancel out. So QED, we have this lemma. Now we look at this quantity. This is basically unnormalized 2-point correlation function, which is also written like this. And yeah, it's this integral here. Okay, and so here we have integration over all theta u. But anyway, this function here is analytic in theta u and also satisfies this periodicity. Okay, so we can use this lemma here to this integration, and to see that this is exactly equal to this. And this is simply obtained by replacing theta w by theta w plus I phi w. And since we can do this for each w, this phi w is just arbitrary. This is arbitrary real quantity. Okay, so this is actually the main thing. So let me write this here. Oh, no. I want to do something more. Okay, so now, so this is what we observed. And now it's easy to see that you have this identity for cosine theta plus I phi. So you just plug this in here to get this. Now here, okay, I note that, okay, so this is from here, and this is a real quantity. This is real quantity. And so this is non-negative. Okay, and this came from part of this thing. part of this, and from here. And here again, you have real coefficient. So this part is just real. So this is again non-negative. And here I put everything inside I. So here you have a pure imaginary thing. So here, yes. So here I have a complex quantity whose absolute value is 1. Okay. And then you can just forget this factor to upper bound this quantity like this. Okay, only these non-negative parts remain, and this is of course rigorous upper bound. You throw that. Of course, this shows non-trivial oscillation, but if you forget about this, you get this upper bound. Okay, now here I have cosine and hyperbolic cosine. Okay, and then again, this is just trivial. You can rewrite this like this. You added cosine and you subtracted cosine here. And then since this part is non-negative, you can, and cosine is upper bounded by 1, you can upper bound this like this. Okay, here you only have hyperbolic cosine phi, and you only have cosine theta. And yes, you apply this inequality here. And then very nicely, this hyperbolic cosine part and cosine part decouples. And since hyperbolic, this phi does not, phi is simply a constant. Okay, phi is anything, so it's a constant. So I can just pull out all these phi outside the integral, and inside the integral, the only thing you have is this. But this is nothing but the definition of the partition function. Okay, so we haven't done anything. We haven't evaluated any integral, but anyway, we get a very meaningful result because z times this is upper bounded by this quantity times z. So this means that we have this lemma. Okay, I call this lemma, but this could be called a theorem. This is a very meaningful result. So the main result is that for any phi, real phi, we have this upper bound. Okay, and surprisingly, this very meaningfully looking result was proved only by the change of variable. Okay, we didn't use anything non-trivial. We just used this lemma and made this substitution, and we bounded this integral by simply bounding this by 1 or bounding this by 1. And so very simple, but finally we have this, and without doing any integral, we got this. Okay, and the question is whether this is meaningful or not, and I claim that this is very meaningful. If you choose phi properly, and this tells you a lot. Okay, and so let's see what is the proper choice of phi w. I mean, I stress that phi are just constants. You can choose them in an arbitrary manner. Okay. Now, so I write the right-hand side of one as like this, where phi is this, and a phi is this. So this is actually not exactly the same as this, but if this difference is small, and if you Taylor expand, then this becomes like this. Okay, and then I want to try maximizing a phi because maximum a phi gives you the best upper bound. Okay, so I differentiate a phi by phi w, and you just compute. You get this delta function and Kronecker delta and this. Okay, and by recalling the definition of lattice Laplacian, you can rewrite it in this form. Okay, now you require that this derivative is 0 to find the maximum, and then the condition you find is this, which is nothing but the Poisson equation that we have seen in part 3, P11. So this is part 3, page 11. Okay, so this is a Poisson equation. Okay, it's if you compare, they have exactly the same form. Okay. So if we choose phi w as the solution so suppose that we choose phi w as the solution of this Poisson equation. And then this is our definition of a phi. And this is just rewriting. We did this before. You can rewrite this by using lattice Laplacian like this, and then you plug this in here to find that this part becomes 1/2 minus 1/2 phi u minus phi v or something like that. So you finally find that this is this. So if you use this form, and then you recall that this right hand, yes, this is basically this. So you find that this 2-point correlation function is upper bounded by this. But again, this recovers exactly the equation 5 in page 10 of part 3, which came from the harmonic approximation. So let's look at this. Yes, this one. So this is a Poisson equation, and this is a bound obtained from the harmonic approximation. So we exactly have recovered this. And here we are discussing rigorous upper bound. Okay. So this is one strategy of using this Maclaurin-Spencer lemma. Okay. So this is valid for any phi. So you can choose this phi as a solution, as the solution of this Poisson equation. But this is not technically easy, because then you have to deal with, you have to evaluate the solution of Poisson equation by using something like k-space integral and something like that. A simpler strategy is that since phi is just arbitrary, you can use simpler and explicit choice of phi w. And this strategy goes, I believe this strategy goes back to Pico. And so we will follow this. So here, this is our choice. So this is reminiscent of the solution of Poisson equation. But anyway, this is our choice. Okay. So this is a constant that we are going to determine later. So this is some constant, and we choose phi like this. Okay. So this is a function of. So I fixed u. Okay. I fixed u, and this is phi w, and then we assume that, okay, so I take this L as distance between u and v, okay? And then I assume that this phi is 0 for large distance, and it depends on w like this in this logarithmic form. So it looks like this. It decreases and stays 0, okay? And then by plugging in, for example, considering, yes, from this, you easily find that phi u, when this is 0, you simply get this is alpha log L, and when w equal v, you have this, and this is 0. Okay, and furthermore, we can show that with this choice, this summation is upper bounded in this form, where c is some constant. Okay, this is a bit tedious, but simply this is easy. I mean, you replace this by phi minus phi squared, and you do simple calculation. You basically get this. So this is not too difficult, and so anyway, we can show this. Then what you find is that this is a basic inequality proved by Maclaurin-Spencer, and then we just substitute this here. And then since v is 0, we only have this. This is this, and this is upper bounded by this. So this part is negative, okay? And this part is of course positive, okay? And this is positive. Now we want this to be negative, but anyway, it can be made negative. So we have this, and since we have log, we have log L here and here, you can rewrite this in this form. L to the power this, okay? Right, so this is what we have proved. And then we want to maximize this upper bound by choosing proper alpha. Way to do that is, of course, we want to have big exponent, negative exponent. So we define eta beta as the maximum of this quantity here. And I argue that this maximum is always strictly positive. You find it by drawing the graph of this thing. Since this depends on alpha squared, proportional to alpha squared, it's like alpha here, and it finally goes down. So there is always okay. The maximum is always strictly positive. Okay. So this is This is beta dependent maximum, but anyway, it's strictly positive. So if you plug this in here, we get this. So, because L is U minus V. Okay. L is U minus V, we get this. So this is our main result. Okay. So we have proven the upper bound which decays with a power law. And you can also easily find that this maximum is attained when hyperbolic sine alpha is 1 over beta theta, beta c. And if you plug this in here, you can write eta, you can write down eta beta explicitly like this. Of course, this doesn't mean much, but for this region of very low temperature, you find that this behaves like this. Okay. So this is the end of the proof, but we still have to show this rather technical upper bound. Okay. Well, this is not too important, but anyway, let's do this. So we shall prove this upper bound. Okay. So let W and W prime be nearest neighbor pair, and I assume that distance satisfies this. And then I consider this difference, and by definition, yes, by definition of this phi, our choice of phi, we have this. And since they are neighboring, this is upper bounded by this plus 1. This. And so this means that this is equal to this, and it's upper bounded like this. Okay. And I also note that this quantity is always upper bounded by constant times x squared when x runs in this range. And this is a very simple inequality. You can prove this by drawing a graph. So this is a graph of hyperbolic cosine x minus 1, and this is alpha. So you just compute this here, and you just draw the, yeah, you just compute this curve ax square, which intersects here, and then you will see this upper bound. Okay, and now since this difference from all this kind of consideration, you find that this difference for this nearest neighbor bounds always satisfies this. So so you can use this upper bound here to write it like this, and then for here I use this upper bound to estimate this like this. Okay, and then we have shown that this sum is upper bounded by sum of this thing. Okay, so this is sum over bonds, and I want to sum over sites. So I just put extra factor here 4. Usually this 2 is enough, but considering the worst case, I just multiplied everything by 4 for the choice of W prime. Okay, so this is not optimal, but this is a rigorous upper bound. And then we want to evaluate this kind of summation. Okay, but this is easy. You can always upper bound this by integral by properly choosing these constants like this. And then this can be evaluated easily to get produce log L. Okay, I put 4 here because I have 4 here. And so for some constant. Okay, so if you plug this in here, you find this. This is our desired upper bound. The proof of the Maclaurin-Spencer theorem is done, but in the remaining 3 pages, I'm going to prove the Hohenberg-Mermin-Wagner theorem by using this Maclaurin-Spencer method. Okay, so now I consider the 2-dimensional XY model under positive magnetic field. And this is our Hamiltonian, this is a partition function, and this is the expectation value. And then here is the theorem. For any beta, the spontaneous magnetization defined like this is vanishing. Okay, so again, this is magnetization density under magnetic field. You take the infinite volume limit, and then you take the limit where magnetic field goes to 0. By using translation invariance, this is the same. And by using this expression, this is something we want to prove. Okay, we want to prove this. Okay, now it's very easy after knowing Maclaurin-Spencer thing. So for the repeating this main beautiful idea by using this complex integral. You can bound this quantity like this. Okay, the proof is essentially the same. Actually, this part is the same. This part is the same, and this part is new. This came from this magnetic field term. Okay, and again, this is valid for any phi, any phi. And here we choose the same phi as before, but before L was determined by u minus v, but in this case we only have site u, so L is for the moment arbitrary. This is an arbitrary constant satisfying this. Okay. Anyway, by substituting this, since this part is exactly the same, we get exactly the same thing with the same eta beta and this extra term. But this is nothing difficult. Since we have this extra thing, I simply sum this over w and substitute phi to get this. Okay, so this is our g. And you may try evaluating this g to get strong result, but I won't do this. I mean, for me, it is just important that this is well defined and just finite. Okay, that is only important for me. Okay, so this is just a finite quantity. Okay, and anyway, we have this upper bound. Then what we do is the following: you take any, you fix any lowercase l. And then for any uppercase L, which is larger than twice the L, and for any h, which is sufficiently small that this is valid. Okay, and what is this choice? Well, this says that simply this is smaller than the half of this. Okay, so if h is small enough that this is valid, and then, of course, this tells you that this is upper bounded by this. Okay, since this is smaller than half of this, you have this. Okay, and then at this stage, since L is arbitrary and h is anything which satisfies this, so you can make h smaller and smaller if you want. So you can show that in this double limit, this is upper bounded by this. Okay, now this is valid for any L. And since L is arbitrary, this can be as small as you want. So this means that this double limit must be vanishing. That's the proof of the Hohenberg-Fermi-Wagner theorem by using Maclaurin-Spencer argument. Okay, so that's all for part 4. Thank you very much for watching.